What's up? In this video I'm covering this new paper called Do Transformers Really Perform Bad for Graph Representation? Introducing the Graphormer model by Zhengshuan Jing, Tianle Kai, Zhengjie Luo, and others from, they did this as an internship at Microsoft Research Asia, basically. So what is cool about this paper is that this is the first time that Transformer has outperformed classical graph neural networks on this important benchmark called OGB large-scale challenge. And the whole point of the paper, the whole idea is to encode structural inductive biases into the transformer model, and they show that by adding 3 of those encodings, they can actually outperform, obviously, those classical GNNs, which is super exciting. Having said that, so basically, we up until now, we knew that transformers are really good for sequence modeling, so they dominated the NLP world. Then recently we had the vision transformer entering the computer vision world, and outperforming like a bunch of different computer vision models. But like the only downside there was that it required a huge amount of pre-training. So like it used 300 million data points to pre-train it. And a couple of days ago, I have also covered this paper where the VIT, the vision transformer, used this sharpness-aware minimization objective to actually not need any pre-training anymore, and it still outperforms resonant baselines, which is really cool. But up until now, up until Graphormer, we didn't have the same thing happening in the GraphML field, where GNNs were dominating pretty much. And so let me just briefly show you how it looks pictorially. So they add 3 encodings. They have this thing called a centrality encoding. They used something called degree centrality. They also add these edge encoding and spatial encoding information directly as a bias before the softmax in the self-attention layer. And those just kind of encode the edge information as well as the structural information into the Graphormer model. And we'll soon see the details, but yeah, that was a high-level picture. So now let's start digging into the paper. So the transformer architecture has become a dominant choice in many domains, such as natural language processing and computer vision. Yet it has not achieved competitive performance on popular leaderboards of graph-level prediction compared to mainstream GNN variants. So just as a small digression here, what graph level means is the following. So if you have a graph, a simple graph here, you can do multiple types of tasks on this graph. You can do node wise, so node level predictions, you can do edge level predictions, or you can do graph level predictions. So a graph level prediction would be if you have a molecule here, if this graph represents a certain molecule. So for the graph level, you take into account all of the node and edge features, and you try to regress maybe the solubility of this molecule. On the other hand, if you had edge prediction, for example, you could have multiple edges here, and these nodes can be maybe drugs, and you're trying to predict the side effect by using the 2 drugs together. And for example, you may regress that this edge has a probability of 0.9. That means that this side effect has a huge probability of occurring. On the other hand, this edge here may be implausible because the probability is only 0.001, for example. And that would be edge level prediction task. But here we're focusing on graph level prediction tasks, and most of the benchmarks actually contain molecules, so that makes sense. Next up, our key insight to utilizing transformer in the graph is the necessity of effectively encoding the structural information of a graph into the model. So what that means is the following. So if you know how transformers work, and you hopefully do, and I'll link the paper somewhere here so you can check it out and understand transformers. Hopefully you do, but like this is a 101. Basically, if we have some sequence of tokens like this, and what transformers do, let me draw another one, is every single token will be attending to each other tokens, including itself. It will be attending to this one, it will be attending to this one, it will be attending to this one. And the same goes for all of the other tokens. And as you can see, what it implicitly assumes is that the underlying data is a fully connected, forms a fully connected graph. So if I can just redraw this in a bit different fashion, like this. And what happens is that transformer assumes that all of these tokens, nodes, whatever they may be, they can be image patches in the case of a vision transformer. They can be like subword tokens in the case of NLP. And so it assumes this structure. But sometimes when you have a molecule, for example, you know that the molecule is connected like this. you know that this is the connection. And you want to somehow encode this information into the transformer. And that's what Graphormer did. And we'll soon see how those exactly look like, but that's the whole point. You want to ingrain the structural information into the transformer to make it more performant. Okay, and finally, many popular GNN variants could be covered as a special cases of Graphormer, and I'll later show you this in the appendix, and I'll explain how this comes to be. Okay, having said that, let me just give you like a brief introduction to GNNs if you're not familiar with them. I have a whole GraphML playlist. You can check it out. I'll link it somewhere here. But like, just let me shortly explain you how this works. So what you usually have is in at least this one family of graph neural networks called MPNNs, so message passing neural networks. You have this aggregation step and you have this combine step. And so let me draw a small graph here, something like this. And what happens is the following. So let me connect these like this. So these are the direct neighbors, and we have some indirect neighbors. So what will happen is that for this, so every single node, so that's the first point, every single node and every single edge will have a certain feature vector associated with it. So why is that? Well, basically, assume you have assume this is these are atoms. So this graph represents a molecule. So this edge, this feature vector may contain the information such as, is this a single bond, is this a double bond, is this an aromatic bond, etc. So there can be, as you can see, useful information encoded directly into the edge feature vector. So what you do is the following. So you have this, as I said, aggregate step. So what that does is the following. So it will take the neighbors, so either the one hop or the multi-hop neighbors, but let's assume we have one hop neighborhood here. So that means that this I node will take into account this vector, this vector, this vector, as well as the edges. And it will somehow aggregate that information. So that may be like a mean. You basically add them up and you just divide them by the number of elements, or like sum or whatever. There can be different aggregation methods. But once you have that, so again, you have the original feature vector here, and you have the one you just formed by aggregation. And now the following step is this combine method. As you can see, so this is the aggregated one, so this is this one, and then you have the original one, that's this one. And you somehow combine them. So they can be maybe via MLP, you just pass them through a multi-layer perceptron, and you form a novel representation here, which will look something like this. Okay? So that will be how graph neural networks roughly work, and you then stack a bunch of these layers together. Finally, you have some, depending on the task, you just have some classification head, whatever, you backprop, you train these weights, and that's it. So that's it. And now there is one more thing. If you want to do graph level prediction, what you usually do is you have this readout function. And what it does, as you can see, it just takes the nodes from the set of nodes of that graph, and you just kind of combine them somehow. So again, you have layer 1, and you do on the layer 1 you do a processing that looks something like this. So you do those kind of aggregations, and you combine them, and you repeat that multiple times. So you have layer 2 all the way up until layer L, whatever that number may be. And then you take the node feature vectors from that layer and you, for example, sum them up, and that will be a readout function. So you have a single vector which you can then use to maybe regress something or whatever. And so that's how the pipeline roughly looks like for graph neural networks. So now, having said that, let me just briefly tell you about the transformer. And as I said, so I won't be delving into details here, but you have a couple of procedures here. So basically first project your feature vectors into these query vectors, into key vectors, into value vectors. Then you find the similarity between the query and the keys, and that will provide you with this attention scores, which then you apply just a softmax, and you then use those attention coefficients to aggregate the value vectors. So that's just a high-level overview. As I said, you can watch my video to understand this. That's not the point of this paper. And now let's start digging into the encodings. That's the meat of this paper. Okay, first up, let's see the centrality encoding. So centrality, node centrality is a really abstract concept. They can be many things, and they concretely use something called degree centrality. We'll see that in a moment. But like the rough notion is that those centrality measures tell you how important a certain node or an edge is in that particular graph. So they say it here in equation 4. The equation 4 is just a transformer equation for like accumulating value vectors. The attention distribution is calculated based on the semantic correlation between nodes. So that's the query keys dot product. However, node centrality, which measures how important a node is in the graph, is usually a strong signal for graph understanding. For example, celebrities who have a huge number of followers are important factors in predicting the trend of a social network. As you can imagine, if Elon Musk tweets something, you can assume that a nice portion of the Twitter graph will be copy-pasting retweeting his content, so you can kind of predict, just because of a single node, you can predict the behavior of many other nodes. So that's a maybe rough intuition for why this works. And as I mentioned, they're using degree centrality, and that's a simple concept. So again, assume you have a node and assume you have some edges. So you have some ingoing edges, you have some outgoing edges here. So what node centrality is, it's the following. So basically the out degree will be 3 here. As you can see, we have 3 edges, so that will mean we have out degree 3, and we'll have 2 ingoing edges. So the degree centrality of the in degree is 2. So that's basically it. So that's the number, that's the measure we want here. So for an influencer node, you'll have like thousands and thousands of these ingoing edges, which kind of signal that it's an important node. And how they include that information into this Graphormer is the following way. So as you can see, this is the original feature vector in your graph. And let me try and draw this. So again, you have a small graph here, and it's connected with some other nodes. And so what happens is the following. You have the original, so this xi, that's the original feature vector, okay? And you add up to that feature vector these additional embeddings. So you basically form, what they do is they form a table which has 2 columns. So one column will correspond to the in degree vectors, and the other will correspond to the out degree vector. And now if you focus on this specific node here, and yeah, assuming this one is maybe in degree, maybe this two is outgoing edge, you can see that we can basically form the degree numbers, and we have 2 for the out degree and we have 1 for the in degree. And so using that information, we can basically index into this embedding table, which is initially just randomly initialized. So what we'll do is we'll have, as you can see here, so this will be 0th slot, 1st slot, 2nd slot. We'll just take this vector here and we'll add it directly to this one. So we'll just add it up to this one. And because we have 1 in degree, we'll go to the in degree column and we'll just index into this one. So this is 1. And we'll take this vector and we'll again add it up to this representation, okay? So as you can see, that's basically what they do. And yeah, they say it here, where z minus and z plus are d-dimensional real-valued vectors, so are learnable embedding vectors specified by the in degree and out degree respectively. So what this roughly does, now you can imagine if you had certain node, which is an influencer node, which had a bunch of these ingoing edges, maybe 1,000, and you had another node that also had 1,000 of these in degree edges, okay? That means that they'll be indexing the very same vector here will be used in both of those, and that kind of can signal to this Graphormer that these are somehow special. That's the rough intuition behind all of this, and behind this first embedding procedure. So the second thing, which is really important, is this spatial encoding. And they say here, concretely for any graph G, we consider a function phi between Vi and Vj. So we have node space, and we had node space, just a Cartesian product, and we map that into real number. So which measures the spatial relation between Vi and Vj in graph G. So this is very abstract. Let's make it a bit more concrete. So in this paper, we choose phi to be the distance of the shortest path. So the shortest path distance between Vi and Vj if the 2 nodes are connected. If not, we set the output of phi to be a special value, for example, -1. Okay, let's see what this practically means. So again, we have this equation. As you can see, this is basically transformer equation, we have just the dot product between, so this is the query vector, this is the key vector, we do a dot product, this is transposed, and we just kind of scale it where d is the number of dimensions in those vectors. We just take a square root. Okay, so this is the transformer part, and that's not that interesting. So what's interesting here is they add a bias. So this is a learnable scalar, as they say here, to encode this information of the structure in the graph. And they do that by, you can see here, this phi is used to index into this B array. So B will be, again, as we had we had this embeddings here, now we'll have similarly array that we'll call B, and which will be able to index using this phi, where phi is the shortest path between any 2 points. So that means the following. Again, let me draw a simple diagram. So we have maybe something like let me draw like a path diagram. So we have a simple path diagram, a path graph, and as you can see, this node here will have, so this node here will have a distance of 1. This node here will have a distance of 2, so that's the shortest path, and finally this one will have distance of 3. So that means when we form a query vector here and key is here, what we'll do is the following. So we'll be adding, so for this particular node here, we'll be adding, let me just change the color. So this is 0, 1, 2, 3. So for this one, we'll be using exactly this one. We'll be using this scalar. Then for the second one, we'll be using this scalar. So now you can imagine that this can help us learn some interesting stuff. So they say here, for example, if B is learned to be a decreasing function with respect to phi, so that what they say is, as we go down this B array, if this becomes like smaller and smaller, so they say that for each node, the model will likely pay more attention to the nodes near it and pay less attention to the nodes far away from it. And in the extreme case, imagine you have maybe 0 here for the first node, and you have -infinity for all of the other ones. So if this is -infinity, what will happen is, because you're adding those to the attention score, after applying softmax, all of those nodes which have -infinity, the attention coefficients will drop to 0, whereas for this one, it will be non-zero, it will be probably 1. So in this particular graph. So we'll be focusing, so what we'll end up doing is focusing on only this node here and ignoring the rest of these. So if we had more neighbors, more direct neighbors, we'd be basically focusing only on the one hop neighborhood just because of this learnable scalar here. So that's the idea there. This is how they encode this structural information of the graph via these shortest path distance scalars. Okay, that's the second important encoding. And the third one and the final one is this edge encoding. And they said here there are mainly 2 edge encoding methods used in previous works. In the first method, the edge features are added to the associated node's features. In the second method, for each node, its associated edge feature will be used together with the node features in the aggregation. However, such ways of using edge feature only propagate the edge information to its associated nodes, which may not be an effective way to leverage edge information in the representation of the whole graph. So, in a nutshell, what this means is the following. So if you have a graph, again, let me draw a simple graph here. What they do is, if you have a graph like this, and when you do those aggregation and combine steps in the first layer of the GNN, what we'll end up doing is we'll end up including this information, so these 2 edges and information from these 2 nodes, into this novel representation that will form here. And we are ignoring these edges here. We're ignoring them in the first pass at least. And what they are suggesting here is that it may be wise to kind of ingrain that information straight away, and like during this aggregation process, just kind of use that edge information from all of the other nodes. And that's how they do that is the following. So again, you can see simple stuff. We have the transformer part, we have the spatial embedding part, which I just explained, and we have this novel edge encoding part, which is this fancy formula, which I'm now going to try to explain. So again, we'll have an embedding table. So we'll have a table which will correspond to these learnable edge features. And like the length of this table will just be the following thing. The length will be the maximum shortest path in the graph. So you find so between every single node in your graph, you find the shortest paths and you find the maximal such path, and that will be the length of this table. Let's call it, I don't know, maybe E. And okay, so once we have that, we do the following thing. So let's assume we want to find, let's assume we're finding a tension score between I and J. So if this is I, and if this node here is J, what we'll do is the following. So we'll have some feature vectors which are associated with these edges, right? So we'll have this and this and this, and we'll do the following. We'll take the first edge, so we'll have edges here. So these are again randomly initialized initially, so we have 1, 2, 3, etc. So we'll take this vector here, we'll do a product between that vector and this vector here. So we'll do the dot product between those two because this is the first edge on the shortest path. So the shortest path is this one. So we have this is the shortest path between I and J. So we'll first do a dot product between those two, then we'll take the following vector, we'll do a dot product between that vector and this vector, and we'll take the third vector because this is the third vector on this path, and we'll do a dot product. And what we'll just do is we'll just sum them up, as you can see here, and divide them by n, which is the number of edges in the path, which is 3 here. So these are the edge features, these are the learnable edge features, and finally just sum them up and divide by n. That's it. And intuitively what this does is we ingrain the edge information across, so between I and J along the shortest path, and they show that in the ablation studies later that this helps boost the performance of the Graphormer model. Okay, so those are the main ideas of this paper, these 3 encodings, and now I'll just, again, so everything else remains the same as in the transformer model. They just ingrain these encodings. Everything else remains the same. You have the multi-head attention submodule. You have the FFN, so the feed-forward network module. You have the layer normalization, standard stuff. So I won't go into those details, and I'll skip this interesting part for now, which shows that classical GNNs can be considered as a special case of this Graphormer module. But before that, let me show you the experiment results. So looking at the baselines here, so again, this is this large-scale challenge data set. It has 3.8 million graphs, so it's huge. Compare that to previous popular GraphML benchmarks such as Quora, CiteSeer, or PubMed, and you'll see that this is much bigger and so a much better benchmark compared to those. And we compare with GCN, so that's Graph Convolutional Network, with GNNs, with GCNs, with the virtual node, etc. And we have, this is some modification of a transformer, also an attempt to apply transformers to graph level prediction tasks, but not as successful as Graphormer, as we'll see. So as you can see, looking at the test, so this is mean absolute error, we achieve, so Graphormer achieves the lowest error compared to all of these other classical GNNs. So those are some nice results. And there's one thing I want to mention here. Let me just see where it is. It basically, as stated in section 3.3, we further find that the proposed Graphormer does not encounter the problem of over-smoothing, i.e. the train and validate error keep going down along with the growth of depth and width of models. So now that this may be strange if you're not familiar with graph neural networks, but basically compared to CNNs where more depth, basically take resonance for example, so the more depth you have, the more expressive and powerful and performant the models are. Here in the GNN literature, basically depth doesn't necessarily help. So you usually see those shallow GNNs like 2 or 3 layer deep, and those work just fine. So the reason for that there are multiple reasons. So one of them is maybe bottleneck. So that means if you take a look at the 1-hop neighborhood, you'll have maybe 100 neighbors. If you take a look at the 2-hop neighborhood, you may end up with 10,000 neighbors. If you take a look at the 3-hop neighborhood, so that's the third layer of the GNN, you'll maybe be attending to millions of nodes. And just if you try and average all of those feature vectors, you'll end up basically collapsing into a single feature vector, and that's something that's called over-smoothing. So basically all of your feature vectors start collapsing into very same representation, and thus you don't don't have the discriminative power to kind of figure out whatever the task at hand is. So maybe predict the solubility of the molecule, whatever. So that's the oversmoothing problem, and it seems that Graphormer kind of dealt with it, and I'd be really exciting. I'm really excited to see like what the future research shows and explains why this is. Finally, they also show some results on other OGB datasets. Again, these are mostly molecular datasets, and you can see again it just outperforms all of the other baselines. This flag is just a simple adversarial augmentation, so that you know what this suffix means. And yeah, on zinc again, lowest mean absolute error compared to the previous baselines. So that's pretty much it. They also did some ablations showing that all of these encodings boost up the performance. So this is the edge encoding. As you can see, the error drops when they add it. Same goes for the no centrality. Same goes for the spatial encoding. They always have these boosts in the performance when they add those particular encodings. Finally, as we know, basically transformers have problem with the scalability. At least the vanilla transformer, we have this quadratic dependency between the tokens because of this attending mechanism, and so the quadratic complexity of the self-attention module restricts Graphormer's application on large graphs, which is pretty much obvious. So that means that even though it achieved really nice results on these benchmarks, which are molecular data sets, molecular graphs, I can imagine that this still can't be used to any like huge graphs, such as maybe social media graph. And so yeah, I just expect to see people kind of using the ideas that came from the transformer literature, like limformer, performer, etc., to kind of make this thing more efficient, and then we'll see whether it can achieve some nice results even on larger graphs. Having said that, those are the main ideas of this paper, and now I want to focus on this fact one and kind of delve a bit deeper into it and explain why this is. Okay, let's focus on this part. By choosing proper weights and distance function phi, the Graphormer layer can represent, aggregate, and combine steps of popular GNN models such as GIN, GCN, and GraphSage. Moreover, we show further that by using our spatial encoding, Graphormer can go beyond classic message-passing GNNs, whose expressive power is no more than the Weisweiler-Lehmann 1 test. So, by the way, there is a bit of confusion about this Weisweiler-Lehmann test, and the thing is, all of these expressivity statements basically only are valid for so-called anonymous graph neural networks, where by anonymous I mean that the node feature vectors are actually basically non-existent, or they are not discriminative. So that means by using standard graph neural networks, you always have those node features, so these analyses are not that, they can be kind of tricky. I'll link this blog down in the description. You can see it on the screen, which explains this problematic really good and kind of explains what GNNs can learn and what they can't learn, and so do check it out. It's really cool. Having said that, let's focus on this part. How can we treat these classical GNNs as a special case? Okay. But let's start first with this Weisweiler-Lehmann thing. So Weisweiler-Lehmann or the color test, basically what it does, it outputs a color histogram, and if the color histograms are the same, it claims that those two graphs are isomorphic. And we can clearly see that these two graphs here are not isomorphic, but Weisweiler-Lehmann tells us that they are isomorphic, because we have 4 red colors and we have 2 blue colors. And because of that, Weisweiler-Lehmann would falsely claim that these are isomorphic. On the other hand, if you focus on the shortest path distance, so let's see what they say here. So these two graphs cannot be distinguished by Weisweiler-Lehmann 1 test, but the SPD sets, i.e. the SPD from each node to others, are different. The two types of nodes in the left graph have SPD sets, as you can see here. And let me explain, kind of break it down for you what this means. So obviously the shortest path distance between this node, this red node, and itself is 0. It has 1 distance until it reaches these nodes, and 2 for these two, and finally 3. And as you can see here, that's 0, 1, 1, 2, 2, 3. And for all of the red nodes, we have the same SPD set, okay? Finally, for this blue node, again, we have trivially 0 shortest path to itself. We have 1, 1, 1 here, so that's 3 1s, so those are these ones here. And finally we have 2, 2, which are these two. And similarly goes for this graph here. And we can see that the SPD sets are different. Thus, this SPD will help us determine that these graphs are not isomorphic, i.e. they are non-isomorphic. So that's like a visual explanation and a particular example where they show that Graphormer is more powerful than those simple like Weisweiler-Lehmann one-test kind of architectures. Okay. Now let's focus on the really important part, and that's these. How can we basically show that some GNNs are special case of this Graphormer module. So let's focus on mean aggregate function and explaining how that works. So we begin by showing that self-attention module with spatial encoding can represent mean aggregation. This is achieved by, in equation 6 setting, so this is equation 6. This is your transformer. This is your basically bias using this shortest path function. Okay, so by setting the scalar when phi equals 1, so direct neighbors, to 0 and to minus infinity otherwise, where phi is the shortest path distance, and setting these two matrices, so the query projection matrix and the key projection matrix, to 0 matrix, and the value projection matrix to identity matrix, then the softmax gives the average representations of the neighbors. And let me try and break it down how this exactly works. It's quite simple. So we have a node here. We have some direct neighbors. Let's say we have 3 direct neighbors, so these are connected. And finally, let's say we have some indirect like neighbors. Okay, like these two. So what happens is the following. So as we know, these will have, and we are focusing on this node and trying to figure out the next layer representation. So we can see that these nodes here have distance 1, and these nodes here have distance 2, and finally 3. Okay. So what I say is the following. If we set these b's to 0, so if we set this one to 0, this one to 0, and this one to 0, and if we set these to minus infinity, then, as you can see, looking at this formula here, we'll have that after we apply softmax, these will get to 0, and these will have some non-zero value. And now the second portion is this. These matrices should be 0 matrices, and the value should be identity. That will help us achieve the mean aggregation over neighbors. So let's see. So for now, we just have some arbitrary non-zero values here, and we have zeros here for the attention coefficients. So now, let me do it like this. So let's focus on this particular node. And so we have some feature vector. Once we map this feature vector using the key, query, and value matrices, we'll get the following things. So query and key, so key and query will just be 0 vectors, because remember we have 0 matrices there. And this one here, because we have an identity matrix, will be the same, just a copy-pasted version of this vector here. So this is V as well. So this is the value vector, okay? And now we do the same thing for all of the nodes in the graph. And as you can see, if we take this query vector, which is all zeros, and we do a dot product between any of the keys, because all of the keys are also all 0 vectors, we'll always have this thing going to 0. So this term in the equation will go to 0. And finally, as I already explained, we'll have this bias terms will be 0 for the local direct neighbors and minus infinity there. So that means we'll basically end up having the same coefficients here, and that's going to be 1 over 3. And these will be 0. So we'll end up attending only these nodes here, and we'll take a mean average of those 3 feature vectors. Okay, so if you're confused by 1, 3, it's pretty simple. So it's just softmaxing. So you'll have E. So let's focus on for example, on this node. We'll have E raised to the power of 0, because that's the attention score we got. And down in the denominator, we'll just have a sum. And that sum will be equal to 3, because we'll have 3 times E raised to the power of 0, and we'll have 2 times e raised to the power of minus infinity, which is obviously 0. And that's why this goes to 1/3. And that means that, yeah, basically those are the attention coefficients that this node will use to accumulate the value vectors of the direct neighbors. And as you can see, we literally achieved this mean aggregation. So that was the first part. Now the sum aggregate part is pretty easy once we understand this first mean aggregate part. But let me zoom in a bit here and explain it. The sum aggregation can be realized by first performing mean aggregation and then multiply the node degrees. We'll see what that means. So specifically, the node degrees can be extracted from centrality encoding, so that's the degree encoding, by an additional head and be concatenated to the representations after mean aggregation. Then the feed-forward network module in Graphormer can represent the function of multiplying the degree of the dimensions of average representations by the universal approximation theorem of fully feed-forward networks. Okay, so let me kind of break that down. It's pretty simple, and I'll just draw it over this chart. So let's assume the first head gives us the mean representation for this vector. Okay, so we have that part. And now what they say is the following. Let's take another head. So we have multiple attention heads. Remember, this is transformer. So what that head will do, it will learn how to extract the degree of this node, which is, as you can see here, just consider it's undirected graph, so it's 3. So we'll learn how to extract maybe something like a vector which will have all zeros and only 3 at the bottom here, okay? And so how that will happen is the following. So remember, this vector here is formed by taking the original vector and adding to it those embeddings for the degree centrality. So basically we'll be adding those vectors which contain the degree information. And this head can learn how to extract from this vector, how to extract this number here. So that head will learn how to do that. And once we have that, we do the following. We basically concatenate, because if you remember how transformer works, every single head, attention head, will basically output a representation. Those will get concatenated, then we'll have some MLPs. So again, we'll have the following. We'll have the mean representation, and we'll have the degree of the node. And then by this theorem of universal approximation theorem, where these MLPs can basically, like, given enough width and depth, they can basically approximate any function. So what we get here is, after mapping them, it can learn how to take this number, let's say 3, and multiply it with every single feature dimension here. So with this thing, with this thing, with this thing, with this thing. And if we do that, we'll just end up with a sum aggregation instead of mean aggregation. And hopefully this was clear enough. This is how I understood it, basically. And yeah, if I'm wrong, feel free to comment down. But yeah, I think that's in a nutshell how it works. So similar thing for max aggregate, similar thing for combine and mean readout. You can do it yourself, but this is the whole logic, the whole point how this works. And yeah, we saw we can emulate these as a special case of Graphormer, and that's super cool. Having said that, if you like this video, consider sharing, subscribe, and until next time, bye bye.